Hello guys, we will just continue our lesson. The topic that I had discussed a while back. So this is the continuation. So we will proceed now for the shear and moment diagram for a frame. So recall that a frame is composed of several connected members that are either fixed or pin connected at their ends. So unlike beams is one straight member, but here is several connected members, and it can be fixed or pin connected at their ends. So the connection between the two adjacent members is either fixed or pin. The design of this structure often requires drawing the shear and moment diagram for each of the members. So usually, to design the frame, you need to draw the shear and moment diagram, because this shear and moment diagram can give you the values, which these values can now use for determining the size, the number of bars, and so on and so forth. This requires first determining the reaction at the frame support, then using the method of section, we find the axial force, shear force, and moment acting at the ends of the member. Provided all loadings are resolved into components acting parallel and perpendicular to the members axis, the shear and moment diagram for each member can be drawn as described previously. So when drawing the moment diagram, one of the two signs is used in practice. In particular, if the frame is made of reinforced concrete, designers often draw the moment diagram positive on the tension side of the frame. In other words, if the moment produces tension on the outer surface of the frame, the moment diagram is drawn positive on this side. Since the concrete has a low tensile strength, it will be possible to tell at a glance on which side of the frame the reinforcement still must be placed. So let's have a typical example. So draw the moment diagram for the tapered frame shown in figure 4-1791. So how will we draw the shear and moment diagram? First, the question here is draw the moment diagram only. A is said to be roller and B is pin, and since C is not indicated whether it is fixed or pin, so usually if that is the case, this will be fixed. Okay, so here what we can do is, the first thing we need to identify here is the support reaction. A is roller, A is roller, B is pin. Meaning, if it is pin at B, there is forces along X and Y. So to determine the summation, the reaction at A is roller, so this is only upward. B is pin, so horizontal and vertical. Okay, so here to determine the horizontal component at reaction at B, summation forces along X is equal to 0. So here the value of the horizontal reaction at B is 3. How about for BY? We can take moment here. 3 times 6, 18 divided by, right? Summation moment at A is 3 times 6 is 18, plus you have reaction here, minus 3 times 11 divided by 15 is 15. So this is 1 downward, and summation forces along Y, 5 plus 1 is 6. So these are now the reactions. Here 6 because this is roller, then you have pin, which is downward 1 keeps, and horizontal going to the left 3 keeps. Now to draw the diagram, you need to isolate, or you need to you cut it by member. So here from member A to C, here. You can assume any point just near, near here at point C, cut. Then the same is true with CB, cut. Okay. So when you cut this one, you have 6, you have 3. Of course, this is said to be fixed connection, fixed connected. So you have moment. You have, of course, summation force along X, 3, 6. Then moment 15, how? Summation moment here is 3 times 15. So it's 15. So whatever reaction you calculated here, you can just adapt here, but you need to reverse the direction. Why you need to reverse? So that when you return it, it will be equilibrium. So here is 3, then 6, and moment. Then this one are now given, then this one. So you can have here summation forces along X, Y, it will be 5 plus 1 minus 6 is 0. Summation forces along X is 3, 3, 3. Summation moment at this point is 6. It will be 15. Okay. By the way, when you perform summing moment here, this is this is said to be infinite length. You cannot consider this one as moment created by moment arm. There is no moment arm here because it's almost nearing to to 0 eh. It's almost not totally 0, but at x distance, but not equal to 0. So meaning we just consider the moment appeared here, so 15, 15. Then of course the same is true. Apply this one, 3, 15. The summation force along x, 3. Summation force along y is 1. There is no moment here because this is pin connected. Now we can now draw the diagram. Consider this one, the moment diagram. You have here downward negative 15. Then here is 0. Okay. So CB, this one. Consider this one, there is no moment. At point this one, there is no moment. Then here, it will be 3 times 5, 15, 15. Then it will counteract by 15, so it will become 0. Okay. So let's have another example. Draw the shear and moment diagram for the frame shown in figure 4-18A. Assume A is pin, C is roller, and B is fixed joint. Neglect the thickness of the member. So what we can see here is this distributed load 0.414 kips per feet is not distributed perpendicularly to the incline BC. So what we can do here is we need to get the component of the horizontal and vertical, because this 0.1414 is not directly directly perpendicular. So we need to get the component of this one along x and y. So 0.1414 cosine 45 degrees is 0.1. So this 0.1 kips per feet will become the perpendicular distributed load acting at member BC. Then 0.1414 sine 45 degrees, the same, it's 0.1, so downward. Okay, so this is now the vertical and horizontal component of the 0.1414. So now, considering this one, before you proceed, you can determine first the reaction. Okay, so C spin, you have x and y reaction. A is A is spin, C is roller, so the reaction is perpendicular at point C. So you can have summation moment at A 0.1414 times 10 divided by 20. Okay? So what will be the value here? 0.1414 times 14.14 feet times 14 divided by 2 divided by 20 is equal to 0.5. Okay? So if this is 0.5, of course, this is also 0.5, the reaction here. And the reaction for Y will become 0.1414 multiplied with the length, which is 14.14. We try with my calculator. 0.1414 times 14. Yeah. 0.1414 times 14.14 is 2. 2 kips. So the reaction at A vertically is 2 kips also. Here, it's 2. Okay. So after determining the support reaction, you can now isolate one member BC. So having this BC, you already get the components of this 0.1414 horizontal and vertical. Then you have 0.5 here. This 0.5 load will be you need to get the components also. So from 0.5 it will become, let it be 0.5, then cut near at point B. So when you cut this one, there will be vertical reaction and there will be normal, then you have moment. Okay, so to identify that one, first you need to get the component of this 0.5. So how we can determine the this is 45 degrees, right? 45. So when we project this one, this is 45. So this will be 0.5 cosine 45. Huh? I don't have my calculator. Wait, I need to check first. Calculator. Yeah. Sorry. Sine 45 times 0.5. So how to determine this 1.77? The horizontal component of 0.5 is 0.5 cosine 45 is 0.35. So the components here is 0.3535 plus 0.1 times 14.14 plus 0.1 times 14.14 is 1.77. That's why the reaction here is 1.77. This is coming from the horizontal component of 0.5, which is 0.5 cosine, 0.5 cosine 45 plus 0.1 times 14.14. That will give you 1.77. How about the reaction along y? For y, it will become 0.1 times 14.14 plus 0.5 cosine. Okay? 0.1, join with me, 0.1 times 14.14 plus 0.5 sine 45. Sorry. The direction of 0.5 is against the direction of this 0.1 kips per feet, right? So, sorry class, made mistake. It will be 0.1 times 14.14 minus, right? Minus the component of 0.5 along y, minus 0.5 sine 45. Okay, again, this is 0.1 times 14.14 minus 0.5 sine 45. It will give you a value of 1.06. So this is 1.06. Okay, then for the moment, you can have here summation moment at this point. It will be what? 0.1 times 14.14 times 14.14 divided by 2 minus, you can use the moment arm directly, minus 0.5 minus 0.5 times the moment arm of this 0.5 is 10. See, 10 minus 10. So this is 5. Again, this is 0.1 times 14.14 times 14.14 divided by 2 minus 0.5 times 10. It will give you 5 kips per feet. So now, whatever values you computed here is you apply here, and just applying the principle of equilibrium to get the reaction here, and whatever the reaction you calculated here is you apply to another member with a different sign convention. I mean, you just reverse the direction here so that it will be equilibrium when you consider the whole structure. So now for the moment diagram, here is 1.06 minus 0.1 times 14.4 is negative 0.354. Okay? Then for the moment, this is x. Okay? 1/2, or just getting the area of this one, minus with this one. And that will be the moment diagram. So here, you have negative 5. Just solve the value of x. So it will be negative 5 plus 1/2. This is x times 1.05. It will give you a values of 0.625. Therefore, this area is also 0.625. So it will become 0. So this is the moment diagram. Here, once we use this one, you apply here, then summation force along x and y to check. But by the way, we already calculated the reaction to n.5, so there's no problem. So to check that one, summation force along y should be 0, 2, 2. Summation force along x, 0.5, 0.5. Okay? So here, the shear is negative 0.5. Then no reaction, so 0 degrees. Then upward positive 0.5, so 0. Next is negative 0.5 times 10 is negative 10. Negative 0.5 times 9 is negative 5, so negative 5. Then this 5 keep per feet will keep this moment diagram to go back to 0 so that it will be equilibrium. Okay? So that's it. So again, wait for another video. We will solve it one by one, okay? Because what I'm just giving to you is simply the overview and the point of reference on how to calculate this one. But I will upload another video which I will solve it by my hand and with my calculator so that you can understand easily. So thank you for listening and watching. So wait for another video.